Hi, welcome, and thank you for joining our first Synergy webinar series where we aim to give you the most complete picture of material characterization using multiple orthogonal techniques, hence the word synergy. Okay, so today's webinar title, Additive Manufacturing, Effective Control of Metal Powder Quality is our very first webinar. There will be more to come, so make sure you join our newsletter, our LinkedIn group, or check back on our website. My name is Julie Chen Nguyen, and I will be facilitating today along with your speakers, Dr. Anderson Bonon, our regional manager from the Particle Characterization Group, and Dr. Matthieu Chausseau, product manager for elemental analysis and thin film. Anderson earned his dual PhD in chemical engineering and chemistry from New York University, whereas Matthieu has a PhD in analytical chemistry plus close to 20 years of industry experience. Among us three, we are proficient in 8 different languages, and just a fun fact. Okay, so I will let our first speaker, Dr. Anderson Bonon, open. Anderson, would you please share our screen? I'm going to go ahead and pass the ball to you now.
Okay, so good morning for all of you guys, and good afternoon for the people who are in the East Coast and or any part of the globe you may be. So thank you, Judy, for the introduction. I'm very happy to start the year doing this webinar with you and also sharing our first Synergy series with Matthieu, which is a good friend of mine. So let's talk a little bit about additive manufacturing. So actually, different from a lot of people think. I mean, we're used to hear about 3D printing or additive manufacture. It sounds something that's very recent, but actually, the early stages of its development, it starts back there and in the 1970s in Japan. So, Dr. Komada was one of the first actually to register some experiments involving 3D printing. It's something that actually he missed the first patent. That's what I meant to say here in the slides. I should correct that. So he started to work with this printing and this idea, and actually he missed the date to file his patent, and he just stopped work with this. And then from there, there was a group of French engineers that started to work in prototyping that was kind of very early stages of stereolithograph, which is when you have a resin that is photosensitive, and then you irradiate a UV light to polymerize, and that's how it was the first stages of its development. And they start to work at this, and actually they give up. They say, okay, there's lack of business perspective, so they didn't see future on that. I mean, it's oddly, right? I mean, as this technology happened with similar to many other technologies in the early beginning, in the early stages of development, people, okay, it looks like a cool idea, but who's going to do that? Who wants to invest in that, right? And later on becomes a boom like it is today. So the first patent and the first instrument was actually commercialized by 3D System Corporation, which is, I have a picture of one of the first for the first system here, which is was also based in this resin that you polymerize irradiating UV light. And move forward, to the beginning of the 90s to the early 90s when you have EOS releasing the new laser melting for metal powders, which was very different from what we have today. And followed by the Sweden group that in 1997 released the Electro beam melting system, which is also was very different, very rudimentary for what we have today. And in the 2000s that we have the boom and start to hear about 3D printing all over the globe. And it started not only printing metal, printing resin, printing with plastic, but also have some cells printing or a scaffold, like we had in the early 2000s, a 3D printing of working kidney. Of course, to transplant that kidney to a person actually took more than 10 years to put it in place, and it's something that is still a lot of development working on. Actually, talking about this application, it's something that I did my PhD on. I was synthesizing biomaterials for medical applications, and a portion of my group was actually using the materials that we were synthesizing to make implants. So actually, you see the picture here of this guy holding. It was one of my PIs holding a skull that was using for surgery planning. On the back here, you have skull that's missing a part. You see this black part was actually, we model the missing part of the skull that actually this patient lost in a car accident. So we made this to replace, and here a year that one of our groups member synthesized. And so the applications for the additive manufacturing is immense, right? For automotive, aerospace, for defense, for like very complex structures would be very hard to achieve using conventional means to do. And an infinity of products for consumers good. Like for me, one of the most important things is like, what do I do when I have my action figures missing their main weapons? Um, you just print it. You just print and paint it. So of course you can print and do it, especially today's is with so easy access to CAD softwares. The applications for all of those are limited. So, but today we're going to talk more specifically about laser printing. I'm sorry, not laser printing, but metal printing. And there's main two systems for printing using metal. So you can either use a laser or electron beam. So you have a chamber that is, if you use the laser system, you're going to be using nitrogen or argon in the chamber, in the printing chamber. Or if it is electron beam, you're going to have vacuum in this chamber, and you have the powder hoppers where you have your metal powders here that will be delivered, and you have a rack that we're going to spread this powder and make a bed, what we call fabrication powder bed. And your heating source will sinterize the particles, which will be actually printing a layer. And the way the printing or the process happens is, okay, you have the first layer deposit, and then your laser goes through and sinterize the powder where it should be and print the first layer. And then the stage move a little bit down, and then you have the sinterization of the second layer, and so on. So at the end of the process, you have your object print here in the bottle, which is, it is brought up, and you see you have a lot of metal powders here that was not used in the printing. So some of them will be remaining free flowing from the object, and this is how an object looks like just after it's printed. So if you transfer that to another chamber that is controlled, because this, for you not to have direct contact with the particles because they're too thin, and you actually vacuum out the residue here. But usually both systems, regardless if you use laser or electron beam, you're going to need to do some sort of treatment. You can either be mechanical treatment or thermal treatment or chemical treatment, or sometimes a combination of all of them to have your object as they were supposed to be used. Just a little bit to talk about the main difference of this technology. So of course, they're both proprietaries as the technology, as the acronyms. And the main difference for them, I mean, they both have the same goal, which is to sinterize the powder. And the way one does is actually using laser, which is more precise than the electron beam. And it requires a very a thinner bed printing layer of 20 to 40 microns, in contrast with the 50, 70 microns from electron beam, which means you're going to have particle size for the powder much more, a little bit smaller for using when you use laser compared for when we use electron beam. And then we have some implications which we'll discuss a little bit later. So usually they expect better surface results when you use laser, but also longer printing times, because the laser you do one point at a time, and with electron beams you have multiple beams simultaneously printing the particle. So you're printing the object. So your printing time in that sense will be faster. But also when you have electron beam, it is required for you to use a very high temperatures, like from 650 or sometimes up to 1,000 Celsius degree, which means it's going to take actually time for you to heat up the system. A lot of energy consumption to keep your printing chamber at that temperature, and also you're going to have to wait this, the printing parts to cool down until you'll be able to remove it, right? And so as we talk about, okay, as we saw how the process work, and as any manufacturing process, there's a lot of test method that you need to perform. And up to recently, we didn't have that many specifications for this product. Just we're using regular test methods that were used for other general purpose. And ASTM put together a list in 2014 for a list of methods for you to use in the fresh material as well as recycle, because it's very important for you to recycle the material and make this manufacturing process actually feasible. You don't throw all the powder that you didn't use. And here I have a list. I would say, as any analytical tool you're going to use, the first step is actually for you to go and get this ASTM actually to know exactly how to sample your material for you to perform your analysis, whatever they're going to be. Because this as a materials that can be very heterogeneous and is very hard to sampling. It is important for you to have a very representability on your sample. So you can trust your results, because this can vary a lot just due to the sampling systems you use. We're going to talk a little bit of some of these applications. We talk about particle size and other techniques. And now I'm going to pass the word to Matthieu, who's going to talk about his techniques.
Thank you, Anderson. Hi, everyone. Thank you, everyone, for attending this webinar. I wanted to discuss a little bit about the elemental composition of the powders that are involved in this additive manufacturing process, because elemental composition will have an impact on the process and also on the final composition of the part manufactured, and then on the mechanical properties of the part. Because of that, monitoring the composition and the possible contamination of the powders is really critical for the whole process. The contamination can happen at multiple levels in the process. It can happen at the manufacturing and the storage of the fresh powder. This fresh powder can oxidize over time. There may be some accidental mix with other powders of different composition, or also the presence of foreign particulate. The recycling also of the powders, as Anderson was showing, we are going to recycle a part of the powder, and this recycling makes the process more exposed to the contamination issues. And since there is no real benchmark for reuse, and the impact on the final product is not well known, it's really important to monitor the fresh powder, of course, but also the powder over the various cycles. There are many different techniques that are available for elemental analysis. You can have ICP-OES, ICP-MS, GDMS, GDOES. They all have advantages and drawbacks, but the more suitable for additive manufacturing are X-ray fluorescence, or XRF, and inorganic elemental analyzers that are dedicated to carbon, sulfur, oxygen, nitrogen, and also hydrogen analysis. Those techniques are also described, as Anderson was showing, by ASTM methods that are related to additive manufacturing that facilitates a lot their implementation in your processes. Let me start with X-ray fluorescence, or XRF. XRF is the technique that requires little to no sample preparation, and that is able to measure qualitatively and quantitatively elements from aluminum to uranium, some systems being able to go down to carbon. The technique is based on the detection of a fluorescent X-ray emitted by the elements after irradiation of the sample with a primary X-ray source. The energy of each X-ray that will be detected is characteristic of elements that will help to do the qualitative analysis, and the intensity is proportional to the number of atoms and then proportional to the concentration in the samples to provide quantitative data. Typically, for powders that are involved in additive manufacturing, a small system, typically benchtop system, able to perform bulk analysis, as shown here, is good enough for the purpose. Having access to higher end system, like that one, that allows for mapping, as you can see some examples of mapping here, is nice to provide some nice pictures where you can also see a little bit the heterogeneity or homogeneity of the powder. Operating an XRF system is really straightforward. You can see on the video here. It's just about opening the cover, positioning the sample, solid, or if it's a powder, it will be in a sample tray, and adjust the position using the visualization screen in the software. From there, as soon as you have located your sample where you want to, you close the door and you just start the analysis into the software. Due to X-ray related regulation, of course, the system will warn you that the source is on. Those are these two red lights you can see. And from there, the analysis will start. The analysis can be done in one step or sometimes two steps to measure major elements at high concentration and eventually lower concentration elements that may require different settings. At the end of the analysis, the system will give you a table with the concentration of each element detected using the fundamental parameter method or the calibration that you performed before. Inorganic elemental analyzers are very different from XRF. They also involve little to no sample preparation, but they are based on the generation of gases from the sample. And then we are going to melt or burn the sample. And then compared to XRF, that is non-destructive, they will be destructive for the sample. For the determination of oxygen, nitrogen, and hydrogen, the sample is introduced into a graphite crucible. This crucible is placed into an impulse furnace under a flow of inert gas. By temperature increase, we are going to produce gases. Nitrogen and hydrogen will produce nitrogen gas and hydrogen gas, while the oxygen will react with the graphite of the crucible to form carbon oxide. All these gases will flow into the system. The oxygen will be detected by CO and CO2 NDIR detector. NDIR stands for non-dispersive infrared, while the nitrogen will be measured using a TCD detector, thermal conductivity detector. You can see here the generation of gases for oxygen, nitrogen, and hydrogen happens the same way in an identical furnace, but in many cases, the hydrogen system is a dedicated one to provide better performance for hydrogen detection and better detection limits than with combined systems that can do all three gases together. In such a setup, the hydrogen will be detected using a TCD detector that is the most sensitive detector for this element. For carbon and sulfur, it will be a little bit different. We are using a ceramic crucible that will be placed in an induction furnace with a flow of oxygen. This flow of oxygen with the increase of temperature will create from carbon and sulfur different gases, and we will create CO2, CO, and also SO2. All these gases will flow into the system and will be detected by NDIR detectors. As for XRF, all the intensities measured by NDIR or TCD detectors are proportional to the quantity measured and then can be related to the concentration, making quantitative determination possible. What you can see here is a video that was shot in our demo lab in New Jersey, and you can see how easy it is to perform analysis. Typically, you have a crucible with a sample that you introduce in the furnace, and you can start the analysis by pressing the button on the instrument or clicking in the software. As soon as you start the analysis, the temperature will rise. You can see the temperature increase here, and the various elements, carbon and sulfur, will be detected by the system. You can see the green curve for the sulfur and the blue one for the carbon here, with values in the 0.3, 0.1% level here. When analysis is done, you can just open the furnace, remove the crucible, and move on to the next sample by placing it on the stand and pressing the button again. The whole operation can be fully automated with an autosampler, and you can see here on the left of the instrument the autosampler that is equipped with a cover. Pretty important, that avoids also the dust from the lab to contaminate your sample. And each crucible here will contain the different samples you want to analyze. The autosampler will be in charge after the analysis of removing the crucible from the stand, discarding it in a specific trash tank, and then taking the next crucible for the analysis and positioning the crucible on the stand. From there, the furnace will close and the analysis will be performed the exact same way we saw in the previous slide. What is really unique for our carbon sulfur analyzer is we are using a very unique and innovative cleaning mechanism that doesn't involve any brush or mechanical device. Because there are no mechanical device, we are saving a lot of time and then we can have a very high throughput. Typically, the analysis time may be maximum 70 seconds. The previous video I showed you, the analysis time was about 40 seconds only. That means you can easily do about 50 samples per hour. But the main advantage is that this new mechanism is very efficient and it can provide up to 200 cycles, potentially up to 500 cycles on some samples without any maintenance needed, because it provides literally dustless operation, as you can see here from the beginning of the first sample to the 500 analysis. You can see there is almost no dust on the system. You need to compare that to a standard system where you see at the beginning it is clean and really quickly you accumulate dust around the crucible and on the crucible stand, requiring typically maintenance after 50 to 100 cycles. Let's look a little bit in detail to this cleaning system. You look at a conventional model. It will use a brush that will require slower mechanical movement. The dust generated during combustion is accumulating on the filter, on the inside of the filter. The gas are going through to be analyzed by the detectors, and then after the analysis, the brush will mechanically remove the dust that will fall down into the crucible and around the crucible, where it will be collected by a vacuum cleaner. There is a lot of dust with this setup that will accumulate on the side, as you saw in the picture before, and that will require this frequent maintenance. With the EMIA series, the whole system was redesigned. The whole cleaning and filter design was totally synced again. And we are using a counterflow of inert gas to remove all the dust that is falling down into the furnace and down into a collection tank that is right under the crucible. And in that case, we have almost no dust. I will not say never, but we have almost no dust even after 200 measurements, leading to improved ease of use, improved throughput, and also improved stability. For oxygen, nitrogen, hydrogen, this is a little bit different. There is a risk of contamination with these elements. It's much easier to contaminate with oxygen and hydrogen than with the carbon and sulfur in a lab. And then we have a specific setup to introduce the flux that may be needed to help the sample to melt and also the sample. We are using a dual, what we call the dual loading system, to drop independently the flux and the sample into the crucible. That means the system will be able to outgas the crucible. Then we will be able to introduce the flux to outgas the flux, and then to introduce the sample to perform the analysis. This will result in a blank reduction and improve the accuracy of the measurement. The system is also including a programmable temperature feature. You can increase the temperature using a ramp, as shown here with the blue line, or with steps of temperature and hold time, or a combination of both. The idea of having programmable temperature is to be able to extract different species of the element. For example, you can see in this example 3 different steps of temperature that helped us to differentiate 3 different forms of oxygen. Typically, the first one will be the contamination, what will be on the outside of the sample or the surface of the sample. But the 2 other peaks may be related of different form of oxides into the sample. Now you can see how it works here. You are introducing the sample on top in the dual loading system. You may use the funnel that is supplied for that. Once the sample is ready to be introduced into the crucible, you can open the furnace, place the crucible on the lower electrode, and from there you can start the analysis. By just pushing the button here, the analysis will start, the furnace will close, and the outgassing steps will begin, and the sample will be introduced when needed for the analysis. Automation is also possible. The system can be equipped with an automatic cleaner and also crucible loader that will be in charge of removing the crucible at the end of the analysis, cleaning the upper and lower electrode, and then taking the next crucible that is happening now on the video. And this next crucible will be installed on the lower electrode so as the analysis of the next sample can happen. And again, if you really have a lot of samples to analyze, you can equip the system with an auto-sampler, and it will allow for fully unattended operation. You can see the flux and the sample that are dropped into the dual loading system. And from there, the analysis will start, outgassing steps. The sample will be introduced when needed. And the software will measure both, in that case, oxygen and nitrogen during the combustion. You can see here nitrogen and hydrogen, oxygen, sorry. Oxygen at about 50 ppm and nitrogen at about 280 ppm. Let me show you now some results we obtained on the various samples that were used for additive manufacturing purposes. What you can see here are some results obtained on a fresh aluminum alloy powder, and those are the measurements we did using XRF and the elemental analyzers. And compared to the specification, and you can immediately see, I put them in red, and you can immediately see that this powder was not matching the required specification, mainly due to contamination in silicon, but also slightly too high values for magnesium and iron that made the aluminum, that is the balance to 100%, too low compared to the specification. Even if not specified, we perform analysis for carbon, sulfur, and hydrogen, and they were all in the high ppm value. And you can see also the interesting thing that even at high ppm value, we had very interesting standard deviation with about only 1 ppm standard deviation for about 38 ppm hydrogen. That is very, very stable, providing very high accuracy even on this type of values. For XRF, we are playing a little bit with the instrument and we perform some mapping. And you can see the different elements mapped over the powder, and you can see some obvious heterogeneity for iron with some dots that were more concentrated in some parts of the powder. Then this analysis was performed with 2 different techniques, several instruments, but overall, in few minutes, we were able to show that the powder should not be introduced in the process, and that really helps to identify issues before starting the process, rather than waiting for the final part to be tested, and most likely in this case, to fail the final test. Here are on this slide some results obtained on TI64 that is commonly used for medical or aerospace applications with very strict specification, and including specification on hydrogen that is known as an origin of embrittlement issues that you want to avoid in many applications. You can see here that a quick analysis shows that the powder can definitely be used in the process. XRF results, but also elemental analyzers results at the same time. And again, even on low ppm values or high even percent values, you can see very good standard deviation, very good accuracy of the inorganic elemental analyzers with about 1 ppm standard deviation at a level of 30 ppm of hydrogen. Last example of powders that was used for initial control was a 316L stainless steel. And again, XRF and elemental analyzer were both showing that the powder can be introduced into the system with no harm, and hopefully a good specification for the final part. And again, we can see very, very good precision on the measurement with even at 7 ppm hydrogen, we were able to achieve a sub ppm precision on the measurement. That's really nice because when you're able to measure at such a precision on low values of hydrogen, you are sure that you will be able to monitor your process and identify any contamination very early if it happens. And the last example I wanted to show and to share with you was the monitoring of the recycled powder. I see with a nice typo on the title of my slide. This was done on fresh alloy and after several cycles. The fresh alloy cycle 0 and also after 9, 13, and 15 cycles into the process. The results on the table were not showing any obvious contamination, and hydrogen remained undetected in all samples. But looking more closely to some elements, you can see for carbon here, there is a spike, and that is significant. And you can see we were jumping from 25 to 35 ppm. That is significant, but it was not confirmed on the cycle 15. And most likely this is due to the homogeneity of the powder and probably the sampling, since we are using only few gram, less than 1 gram, to perform the analysis for carbon. If you look at oxygen, it's a little bit different. And the closer look show a high concentration on the initial powder at 290 ppm. And then after, all the analysis were lower than this initial concentration, but with a steady increase. From cycle 9 to 15, we are ranging from 2 ton to 250 ppm. That is a significant difference. There is an explanation. We needed to do some additional analysis, and we are not able to do them because we didn't have enough samples. But most likely what happens here, we may have oxygen at the surface. That is the contamination that disappear during the first cycles of the process. But the steady increase here is most likely an oxidation of the powder over time. And that is definitely something you want to monitor closely because it will affect sooner or later, it will affect the final part and the process itself. I will let now Anderson continue the discussion and show more the particle size point of view for monitoring these powders.
Thank you, Matthieu. And actually, the reason why you ran out of the samples, it was because you needed to send it to me. So I can perform some particle size. So I'm sorry for that, but that oxygen result is actually great because it shows, actually, this is one of the main concern. As we said, depends if you're using laser or if you're using electrobeam. And those samples, if I'm not mistaken, they were recycled in a printer that used electrobeam. So it means it was in the vacuum. So vacuum doesn't remove actually completely the oxygen there. It's different from laser where you completely remove the air present and then you sinterize in argon, which reduce the amount of oxygen, which of course it causes rust and defects in the metal powder that is remaining in the vat. So moving to particle size, right? We talk a lot about chemical composition and particle size is actually a physical characterization of the particles, right? And the reason why it's important actually for many different materials, because up to 80% of the final characteristic of a material is based on the particle size distribution, not in the chemical composition. Now that is not important, but the particle size plays a huge role in the performance of the final material. So I made a list here of one of the main properties that we can follow using the particle size distribution. So when you decrease the particle size, you increase the homogeneity of your sample, you decrease the elastic behavior, which means the particle will be more concise, it'll be harder, but also easier to break. They're going to increase the resistance, and something also comes to powders, like when you decrease the particle size, you also increase the brightness of the material and increase the possibility of agglomeration. So when we talk about particle size, it is a huge range of sizes that we're talking, from angstroms to atoms to microns of emulsions, millimeters for some crystals, up to rocks for mining. So obviously there's no a single technique that is able to measure all the size distribution in one single shot. So we have we have three main techniques that are here, which are the microscopies, right? So we have optical microscopy, and we have scanning and transmission electron microscopy, which covers a huge range, but is very laborious. It requires a lot of sample prep, and it is expensive analysis to run. And even though you of course it's better when you take a picture of your particle, but you also don't count, you have very limitations in the amount of particles you actually analyzing when you run a microscopy analysis, right? You're not measuring thousands of particles by microscopy, counting one by one. And then it comes for sieving, which is the first technique that was created to measure particle size distribution, which also it is a lot of work to do. It's very limited. It has a very limited resolution because the resolution is limited to the sieves you have. And even if you have all the possible sieves, you're still going to have like a very cranky resolution. And some sievings, when you go to lower size, you need to do wet sieving, which it completely changes the characteristics of your sample. So the technique that we're going to talk today is the laser diffraction, because this is the one that ISO recommends for us to use for additive manufactured powder. And it has a huge measurement range. It goes from 10 nanometers up to 5 millimeters. And with this technique, you can analyze powders, suspension, emulsions, some cells, aggregates, proteins. So all kind of samples you can analyze with laser diffraction. So the main concept of this technique, you have your particles in suspension. In this case here, we're using a suspension in liquid. And when your particles pass through laser beams, they will scatter the light in multiple angles. So all the intensities that they are detected in different angles are used to calculate a diffraction pattern, which is unique for every particle size. And in this case here, I'm using the flow cell, which is I made this animation to show how exactly we did these studies that we're going to show, because that's the system what we use for the metal powders. But you also have different ways for you to disperse your sample, and that is mainly due to your main sample properties. Some samples allow you to measure in different ways, some doesn't. you have it works better in one of the ways. So you can use a dry cell, which means you're not going to be using a liquid to do dispersion. You're going to do dispersion in air, or the flow cell, which is the one we use, or we can use a fraction cell, which has a very small volume, about 10 or 5 millimeters, mLs of liquid. So for pharmaceutical, it has very precious samples. They have a very limited amount of sample. Diffraction cell is a way for you to reduce even more the amount of sample that is needed for you to measure the distribution. Or if you need to disperse in a high viscosity medium, then we can use a base cell. Or if you want to, for some materials that you cannot dilute for you to run your samples, then we can use the HL cell because it has a spacer in the middle, so you can use a very small quantity of sample and you don't need to dilute your sample. And also an accessory has a camera that is actually connected in series with the flow cell that takes pictures and allows you to do a dynamic image analysis as well as you do the laser diffraction, so you can have some morphology. So as I saw, we have people here with different backgrounds experience. So we're just going to use this example, these are the results for the fresh sample, and kind of illustrate for us how to interpret the particle size results. And this is something that should be basic, but it's always mistaken in this industry. It is particle size distribution. It's not only particle size, which means it's not a number that actually is going to reflect and describe your sample. So here we see a triplicate of measurement and samples, which means we have 9 results here. So you can see the repeatability of this analysis it's very, very good. So one of the main results what we have is the median size of your particles, which is also called the D50. In this case, for the fresh sample was 22.4 microns. And ISO also recommends for us to follow the limits from 10% of your sample, which reflects the lower portion of your distribution, and the larger particles, the larger portion of your distribution, the D90, which in this case was 31.1 microns. So when you have 3 values, we can calculate something that is called span. So span is a relation for the D10, D90, and D50 that give us a dimensional number that reflects how broad is your particle size distribution. Those all 4 numbers is very important for you to keep track of the performance of your material, because you can have very different materials with the same D50, but with very different D10 and D90s, which will be reflected in the span. So here, comparing the same samples that Matthieu showed the results for oxidation in other examples and in his analysis. So we run particle size in the fresh sample, the sample with 9 cycles, 13 cycles, and 15 cycles. And we see an increment of 17.3 microns from the fresh sample to the 15 cycles. And this is 27.6% of changing your G50, which is a huge shift in particle size. So here I'm plotting all the data, and Matthieu was talking about heterogeneity of the sample, especially when you increase in recycles. So when you have established methodology, you can trust your coefficients of variance, like as you can see here. For the fresh sample, their repeatability is really good, so the coefficients of variance is low, right, 2%. And you see this, it starts to increase a little bit, especially when it goes to larger sizes for the recycles, which mean the homogeneity of your sample, it's not that good anymore. Again, this comes back for what ISO has a specific way for you to sample your material to increase the representability of the sample you're doing. And I have in this plot here all the D10, D15, D90, and the span, so we can track, okay, how much we shift, and we can clearly see as we increase the cyclings how much the standard deviation increased. But the proper way for you to evaluate those 4 numbers is actually plot the span separately. Because of the scale, it may give you a false impression. So first, let's look for the sizes. And we see here the D50 was black. All the sizes had an increase. And the D90 has a very steep increase from the fresh to 9 cycle and kind of gets stable afterwards, but not the D10. The D10 it's almost a linear increment in size. Which means, okay, if you have one size change, one of the size change and one of them doesn't, we can see that's very clear here on the span. So we have a span of almost 0.8, and then actually increased a little bit and decreased drastically. So this decrease means you're narrowing your particle size distribution. So narrowing your particle size distribution, it means, okay, most of the particles are getting closer in size, which is not necessarily a good thing. It can be a good thing when you, let's say, if you're doing a pharmaceutical ingredient that you want, or any other chemical that you want to control the speed of the chemical reaction. So of course, as narrow is the particle size distribution, more homogeneous the reaction is going to be. This is exactly what happens to airbags powders. But in case of materials, you want to compact the material. So you want this material to have a broader distribution so you can use the different size to fill the gaps between the particles. So when we look to the pictures we took of the particles, it is clear for us why this is happening. So we can see here the particles are almost free fall. We have some some stick particles that are non-spherical. So we have the average roundness here of 0.619. And you can see a lot of very small particles. The scale here is 30 microns. So you can see we have a lot of small dots here, and most of the particles, you can see they're free particles. And then as you increase the recycles, you see how those particles, the small particles actually they disappear because they actually getting attached to the surface of the other particles, forming satellite particles. And eventually you have like fusion of larger particles, then you have those particles with like more elongated shapes. That's why we have the decrease from roundness from 0.6 to 0.05. And this causes a lot of defect in your print, in the final printed object. Matthieu, now I would like to move forward for our conclusions.
Yep, I'm back.
Evaluation. Gonna start if your portion.
Yeah, then I will keep on your slide since it's the last slide, I guess. Then, yeah, as we are discussing at the beginning, the quality of the final product is really related to the quality of the fresh powder and also its recycle as recommended by the ASTM norm. And the elemental composition is impacted the mechanical properties. The particle size is affecting not only the process, but also the properties of the final product. And as we saw along the recycling, we see some evolution of the content and also on the particle size shape side of the sample that happens due to contamination over the process and to the evolution of the powder characteristics. For elemental analysis, definitely the X-ray fluorescence and inorganic elemental analyzers are really appropriate and really easy to use for additive manufacturing, both for the raw material, the fresh powder, and also the process control, and typically will provide results within minutes. And both techniques are involving minimal to no sample preparation, and that can be really used for R&D purposes as well as for industrial lab or QC in factories, and be really close to the process. Then the efficiency of the process, the efficient and the quality of the final part can definitely be ensured and improved thanks to the appropriate quality control of the powders, as it can help to anticipate action in the process. And of course, I was saying at the beginning, there is no benchmark on the reuse and no real knowledge of how the final product will be impacted right away. But we can build experience, and from return on experience and benchmark our own benchmark, we can establish this benchmark on the reuse and its effect and anticipate even better the final product.
And it comes to the particle size. I remember in the beginning, one thing about what we saw about the shape, when the particles start actually to melt into each other, of course, you're going to lose a lot of resolution, and you're going to have like an object that is printed with empty spaces sometimes in between because of the shapes of the particles. So your final object is not as solid as you'd like it to be. And also remember when we were talking about the powder bed on the printing, there are specifications, right? For the if you're using laser, if you're using electron beam. So for the lasers from 20 to 40, and for electron beam is from 70 to from 50 to 70 nanometers. So if your particles grows too much and they surpass this threshold of limits, I'm sorry, it's time to. It's of course we don't want to lose that, but it's time for you to recycle. And as Matthieu said, unfortunately, there's no specifications for how much actually you can recycle, because that would be very depending of what kind of object you are manufacturing. So this is something that it needs to be tested in-house, which will be the limit for a specific project or for a specific object in question that you want to print. Based on that, actually, you're going to establish your own parameters and when you should stop to recycle your materials.
Well, thank you so much, Anderson and Matthieu, for this excellent webinar. Let's go ahead and move on to the Q&A session. We still have some time left, so feel free to turn on your webcam whenever you're ready. Let me see. So let's start with Matthieu, if possible. So the question is, how is the powder sample prepared for XRF analysis? And part 2 of that question is, would you use loose powder or press the powder into a puck?
Yeah, in that specific case, the powder were placed into a plastic tray. We made the holder from a plastic tray and just maintained under partial vacuum. So there was no specific pelletizing operation made for the powder. It was pretty straightforward.
Got it. So the energy dispersive XRF versus wavelength dispersive XRF, which kind of setup is recommended for stainless steel powders?
Alors, if you look at to the ASTM list, most likely the WD-XRF will be mentioned. All experiments here are made using ED-XRF. The benefit you can have with WD-XRF will be the resolution. It's higher resolution than ED-XRF, meaning that you will be able to detect better, I would say, low concentration elements in the matrix and have better detection limit. But in the specific case of the stainless steel we were measuring here, the specifications are all on pretty high concentration elements. Then ED-XRF can easily do the job. And typically that will be, faster analysis than WD-XRF.
Thank you, Matthieu. Anderson, how do you choose between laser diffraction and imaging analysis when we are detecting oversized particles?
Okay, yes, they're actually very complementary. For you to detect oversized particle, the dynamic image analysis is a little bit more precise than laser diffraction. But when you're going for the small particles, then it will be a little bit of reverse, because you can get a much better dispersion for the metal powders in laser diffraction than you do for image. So if you want to quantify very precisely the threshold of your larger particles, then dynamic analysis would be a little bit better.
Thank you. Can you comment a little bit about that image? I think this person's referring to the slide that you show for the camera.
Okay, let me
And then part 2 of that question is, would color of the laser make a difference to the particle size data obtained on the same sample?
But do you think that the person is talking about actually the image? Can you repeat?
So there are 2-part questions.
Okay. I mean, this image was taken with a dynamic image analyzer. So it was because we didn't have our camera on site when we were measuring the powders. So I made a summary here of the particles. So here we have this distribution that you see here is not just a roundness distribution, because dynamic image analysis generates a lot of data. So we didn't have time to discuss most of them, but analyzing the portion of the sample that has the portion of your sample who has round spherical particles, which usually we consider, like I put here, like as close as you get to 1, more spherical your particle is. And here we see the decrease in roundness of your particles. So that's why you see, okay, and of course, this is what I applied here was just the average roundness, but as the same as the particle size, we can have like the D50 any cumulative results for shape as well. And that's how we can actually quantify how much, what is the percentage of your particles has a specific shape regardless of the size, which unfortunately this data is not here in this picture. So the other question was about the wavelength of the laser, right?
The color of the laser, does it make a difference to the data?
It does, but it does in a way that actually, in this case, so the reason why we have 2 different sources, light sources, is because, let me enlarge here. So there's an optimal intensity of scattering that is due to the laser, that is due to the wavelength of the light and the diameter of the particle. So when you have larger particles, we talk about 1 micron or more, you're going to scatter mainly laser, mainly laser. So the data you have for those particles mainly will come from laser diffraction from the red laser. and as smaller as your particle get, they will start to scatter more the blue light. In the case of our analyzer, we measure all the particles with all the light sources at the same. So you have a compilation of results of all. And there's no specific threshold of particles, that's a limit threshold of particles. It's like more kind of a range. So one particle is stopping, like it doesn't stop right away, right? It's decreased the intensity of laser, it's scatter, and then starts to increase the blue. And as you can see here in this plot, the backscatter detectors mainly scatter the blue light, only scatter the blue light. We don't have red laser scattering in the backscattering detectors. And the reason why it happens actually in physics, as you decrease the particle size, you increase the angle of scattering. So that's why when you have the small particles, they mainly scatter the blue light and only in high angles. That's why we have this here. And we don't have any laser scattering, red laser scattering in right angles. So I'm not sure if this was clarified too much your question, but your question was like, what was the difference we measured with one laser of the other? The difference actually is not the most appropriate size, but the instrument actually picks it automatically. It measures with both and makes a convolution of all the results. So you don't need to worry about, okay, do I need to set up my analyzer to read one light source after the other, even though we have this option. But the reason why we have options to shut down one of the light sources is if when you work with a pigment or a sample that it has a very high absorption of one of the wavelengths, that is the only case that we would turn one of the light sources off.
Thank you. And the next one, so the person says, thank you, that was helpful.
Okay.
How do you check for effectiveness of dispersion in water? How is a surfactant used or added to the sample?
In this case, for metal powders, I'm sorry, can you see my screen?
Yes.
Okay, so in this case, we actually use ethanol. IPA, I'm sorry, isopropanol. I can open real quick here. So for you to know, actually something that you need to test. What is the appropriate dispersion? The best thing to do is actually, before you put that in your analyzer, you get a beaker and then you add a little bit of the medium you want to use as dispersion, and then you pour a little bit of your sample there. And it's visual. It's a visual thing. You see if it forms like agglomerates, if sedimentates, or if it's like swimming, the particles keep swimming in the surface, so you can see what happens with the particles. So you definitely want to do this test before you start, before you put the sample into the analyzer. And then if you see if you have a decent dispersion, you can go ahead and measure and compare if you want, and then you compare results in different, which is exactly what I'm looking for to show here. You have the results in different mediums. For example, as long as you have a good dispersion, you have a very repeatable data. So here I have aluminum, which is a very easy material for you to disperse. And you see here I have in the dry dispersion, comparing dry dispersion, dispersing in water and in ethanol and IPA. So here it triplicates results. I mean, actually 9 runs for every sample in every dispersion medium, including the dry. And here I have a summary of this data. So you can see summarizing the data in water, dry dispersion, ethanol, or IPA. It had a very low standard deviation, and also very low coefficients of variance, which show, okay, any of those mediums would be good enough for me to disperse my particles. And of course, I would be, okay, if I have those options, if I have the luxurious of choose, okay, I can disperse well in all these mediums. So what would go? Of course, water, because you don't have a hassle to do waste treatment, and it's cheaper. Or if you have the dry accessory, you can go ahead and measure the sample dry. And unfortunately, this is not the case for a majority of the samples. That's going to have like a very good dispersion in different mediums, and it's going to be clear when you don't have. So even though you try, let's say, the main mediums that you found that would be good for you to disperse the sample, it doesn't mean you're using organic solvents like alcohol that you don't need to use a surfactant. For some metal powders, this one that we measure, I didn't need to use, but some of them you still need to use surfactant, even though you're using IPA as dispersion medium. So it's something you definitely need to test. And it's clear because when you're measuring the sample, so laser diffraction has this ability for you put it on the wet system, right? You put the sample once, and then you have the sample circulation. You can take as many measurements as you want, and they should be extremely repeatable. because you have the same set of particles running through the system. If you see they're jumping and you have some bumps on the shoulders, they're not consistent at all, it means your particles are not well dispersed. You may have the right dispersion, but you may lacking a surfactant.
Thank you, Anderson. So I'll give it one more minute before we wrap up. You know, they say on average, researchers use 4 to 5 different methods and techniques to characterize their sample. So it's definitely very useful to be able to see it from a different perspective, from elemental analysis to particle size analysis to shape distribution. Okay, so I think that's it for today. If you have any questions, feel free to send us an email or follow-up questions to labinfo@horiba.com. Don't hesitate to tell us what you think about it.
Yes, and I'll leave here our emails if you want to note again. So you can, of course, reach us at any time, me and Dr. Matthieu, if you have any specific questions. And as you said, you know, we have a long list of methods like the STM list about 35 different methodologies to evaluate the metapowders. So it's a lot of analysis to do.
Thank you. For now, have a great day. Thank you, Matthieu, and thank you, Anderson. We will see you at one or more of our future webinars.
Okay, thank you, Judy. Thank you, Matthieu.
Thank you.
Thank you, everyone.
Bye. Bye,
Thank you, everyone. Bye.
everyone.